Welcome back. So in the previous lessons, we discussed the intuition behind SVM. We discussed the hard and the soft margins in the SVM. We discussed the C hyperparameter, the kernel trick, and the kernel types. Now, let's start going into a hands-on experience, and we will start this with SVM with linear dataset, right? So let's start here. Okay. So we are going to work with the Iris dataset, and the first step is of course loading the dataset. So from the datasets in sklearn, we are going to load Iris. We did this before, and we are going to get the data, the first, all the rows and the first two columns, right? And after that, or the first column and the third column, right? We are going to import the first column and the third column, okay? And for y is basically iris.target, right? The labels. And we are going to import from mlextend. This is the library we used right here, or we imported right here, right? We are going to import a function called shuffle arrays unison, right? So we are going to import this function right here, okay? And let's look at the documentation for this function. So if we hover over here, you will see shuffle numpy arrays in unison, right? So it takes the arrays, and the arrays are basically numpy arrays, list of numpy arrays, and the random seed is by default none. So we are going to set the random seed to anything, right? But we are going to use the same random seed throughout the code, right? So when we shuffle the arrays, we have the same shuffle or the same random splits each time, right? So let's take a look here. It will return the shuffled arrays. So this function will basically shuffle the numpy arrays. And this is an example here if you want to take a look, right? So it will return x and y after shuffling. And then we are going to scale x, right? So we are going to use the standard scaler to standardize the features. And the standard scaler, if you remember, standardize the features by removing the mean and scaling to unit variance. And the standard score of a sample x is calculated as follows, right? X minus u over s, and u is basically the mean of the training samples, or 0 of with mean equal false, but we use by default with mean equal true, right? And s is the standard deviation, right? So here we are going to create an object of the standard scaler, and then we are going to use the method fet inside this object on the x data, right? And then we are going to use the transform in order to transform the features, right? Transform x from unstandardized data into standardized data, and then we are going to have x train and x test, right? So we are going to have the first 100 examples to be for training, and then from 100 to the rest for testing. So let's run this, okay? Now after we prepare the data just like this, we train the classifier. We are not going to implement the SVM from scratch because we need to implement the kernels, and we need to have the algorithm very efficient, work properly, and we need a lot of mathematics, understanding mathematics to implement the algorithm from scratch. And anyway, we are going to use the built-in library, right? So we understand the concept of the SVM. Now let's see how we can use the sklearn library to fit a data using SVM, right? So here we have SVC, right? So if we take a look here, C support vector classification, right? So this is short for support vector classification, and this implementation from sklearn actually based on lib SVM. So this is another library, right? And this library is dedicated for SVM. So sklearn is using this implementation, and as we can see, this is the documentation for the library if you are interested to read more, right? The most two important hyperparameters are of course the C, right? The C hyperparameter, and the kernel itself. Which kernel we want to choose, and the degree of the kernel. We have the gamma, we have many other hyperparameters, but the most important two are the C and the kernel. So if we take a look here, if we take a look at the hyperparameters, you can see that C is the regularization parameter. The strength of the regularization is inversely proportional to C, okay? Must be strictly positive. The penalty is squared L2 penalty. By default, C is 1, right? And we can decrease this C or increase it depending on how much regularization we want. Okay, and we cannot really have it as negative. It should be at least 0, right? So it's 0 or more, and we know this from the constraints for the optimization function. And for the kernel, we have here the default one is RBF, right? Radial basis function, and we can use the linear, the polynomial, the RBF, the sigmoid, or pre-computed. Okay, or you can have your own kernel and you can call this kernel or call this function, right? By default it will be RBF. So let's run this, right? So we have SVM equal SVZ C equal 0.5 and kernel is linear, and then we use the fit function on the X train and Y train, and you can see all the hyperparameters here. Now, in order to understand the SVM better, we are going to use a function from the MLXtend library we imported before called plot decision regions. Okay, so this function is specifically made for plotting decision regions, right? So plot decision regions of a classifier. Please note that this function assumes that the class labels are labels consequently, right? So 0, 1, 2, 3, 4, 5, and so on. Okay, and you can read the documentation here. The most important 3 parameters are X, right? The X train, Y, the labels, and CLF is the classifier. So if we take a look at CLF here, you will see classifier object must have a predict method. So you need to use the sklearn implementation, right? Or implement your own SVM, but you need to have a predict method in your own implementation. Okay, and we have the legend, right? So if we take a look at the legend also, you will see that for the legend we have, let's take a look here, we have the legend by default is 1, right? So if we take a look at the legend, integer to specify the legend location. So no legend if legend is 0. So by default it's 1, and you can change the legend location by changing the number here. So 0, 1, 2, and so on. And after that, I will just add to the X label the sepal length, and to the Y label the beta length. Okay, and the title is of course SVM on Iris. So if we run this, you can see the plot here, right? This is from this function, plot decision regions, X train and Y train, and we have the decision boundaries, right? So you can see here we have the triangles as 1, right? And 0 is corresponding to these rectangles, and for 2 we have the circles, right? So this is class number 2, right? This is class number 1, and this is class number 0, and you can see that the decision regions are colored. So this means anything here is considered as class 0, anything in this region is class 1, and anything in this region is class 2, right? So you know from before that Iris dataset is actually linear dataset. It's a linear dataset, right? So we don't really need anything more complex than the linear kernel. So using the linear kernel, we can split the data, or we can classify the data, or have a very good decision boundary with no problems, right? We can have a very good accuracy using a linear kernel. Now, if we try other different combinations, so here we are using grid spec, right? And we import from grid spec 2x2, so we want a 2x2 subplot, and here we change the figure size, right, in order to be more clear. And after that, as you can see, the first classifier is SVZ with C equal 0.1, the kernel is linear, and then we change the value of C, and the same kernel we change the value of C with a polynomial kernel, we change the value of C with the RBF kernel. And as you can see here, we can also have some keyword arguments, right, for the scatter plot. So C equal 50, label equal test data, alpha equal 0.7. So you can take a look at this function, right, plot decision regions function, or the documentation, and see what we can change or optimize here in order to have a better visualization, right? So we have the labels. These are the labels. So the first label is C equal 0.1 linear equal kernel, and the second label is C equal 2 linear equal kernel, and the kernel is linear, and so on, right? So what we are going to do is that we are going to loop over, right, the classifiers, the labels, and from iteration tools, we are going to loop over the grids. So the first time we are going to have 0, 0, and then we are going to have 0, 1, and then 1, 0, and then 1, 1, right? So this is how we do it the most efficient way, using this line, right? So the first time we'll have here 0, 1, 0, 0, sorry, and then 0, 1, 1, 0, and then 1, 1, right? We are going to fit the current classifier on the X train and Y train, and after that we are going to plot using the subplot function from matplotlib this grid and this grid, right? And then we are going to use plot decision regions, okay? And then we have the title for this current subplot. So as you can see here, we have 4 subplots. Here we have c equal 0.1 and the kernel is linear, and c equal 10, the kernel is also linear, c equal 20 with polynomial kernel, and c equal 20 with a RPF kernel, okay? So what you can see here, or what you can notice from these graphs, is that using the linear kernel, we have the data actually pretty good, right? We can split the data and we can have a decision boundaries, right, corresponding to the actual distribution of the data, right? If we decrease C so much, then as you can see, the accuracy is much worse, right? So we need to tune C. We don't really need to tune the kernel itself. We don't really need to check other combinations of kernels, okay? But why we are checking other combinations of kernel? Because if we choose a polynomial kernel or an RPF kernel, then as you can see, what will happen is that we will have a clear sign of overfitting, right? This is the decision boundaries right now using the polynomial kernel, and it doesn't really represent how the data is distributed. And the same for the RPF, right? The RPF can be a little bit better than the polynomial kernel, but both of them are not good at all compared to the linear kernel. So what we can learn from this is that if you have a linear dataset, then it's better to use a linear kernel also. It doesn't really make any sense if you have a linear dataset to use an RPF or a polynomial kernel, okay? So increasing, and we can see also that increasing C increases the bias, reduces the variance, so we become more tolerant to violations to the margin, so the margin will be wider, right? So if we increase C, right, you can see that the margin is wider. If we decrease C, then the margin will be narrower and narrower, okay? So this is very important. You need to understand how we can use SVM with linear datasets. So what do you mean exactly by linear datasets? Linear datasets are basically datasets that we can split or classify or have decision boundaries, and these decision boundaries are linear. So we don't really want to go into polynomial kernels or RPF kernels. So in the next lesson, we will see how we can use SVM with a non-linear dataset, right? So we are going to use 2 datasets actually to visualize everything and see, is the linear kernel good enough, or maybe we need the polynomial, and compare the performance of the polynomial kernel with the performance of the RPF kernel. So let's go to the next lesson and see all this.